Hi, my name is Yutaka Tokuda, XR researcher at KDDI Research Inc. I'm very excited to present our work, Painting Inferno Novel Heat and Stiffness Control Method with Carbon Nanomaterial Conductive Heating Paint. This work was supported by Tatsuya Kobayashi. Heat has been used in many areas of HCI research. For instance, a variety of wearable and ambient thermochromic displays have been investigated by controlling the thermochromic in color based on temperature. Media artists and XR researchers have explored the thermal sensation in multimodal interface to enhance the reality of digital image and virtual object. With the emergence of the FDM 3D printer, heat has become a popular medium to customize the shape of 3D printed structure and is often used as a stimulus to transform multiple shapes in human-material interaction. Thermoelectric Peltier module, thermofluid system, and Joule heating circuit have been used as common heating methods. However, there remains critical issues. For instance, Peltier module is bulky and not flexible. It is also expensive to scale the number of units. The thermofluid system has been used in flexible thermal interface and flexible thermochromic display. However, we need external water bath and a complex fluid control system, which makes it difficult to build a compact built-in heater. Joule heating has become the most popular approach for flexible and embeddable heaters. However, the fabrication of heating circuit is difficult to design complex shape. Uneven heating and limited heating speed remains a problem in thermochromic display and human material interaction. To address these issues, we explore the possibility of the carbon nanomaterial Joule heater as an alternative method. Carbon nanomaterial heating paint is highly electrically conductive ink and can rapidly radiate heat from the painted area by applying current. Since it is low cost and applicable to various materials, it has been widely used in heatable wool and antifreeze applications. We investigated this high potential capability to open up new opportunity in the HCI research field. Among many commercially available heating paint, we investigated Carboethan PUR70 because it is flexible, inexpensive, and safe water-based ink. The fabrication of the heater is very simple. In the following example, we used conductive copper tape as the electrode and 2 cm by 1 cm copy paper as a heating substrate. First, attach the copper tape electrode and power cable to the side of the paper. Then brush both electrode and paper evenly with heating paint. Dry the paint with heat gun around 10 seconds. Finally, to protect the painted surface from damage, apply insulating silicone spray. By applying voltage, you can check the painted area rapidly heat up in a few seconds. We compare the thermal performance of carbon nanomaterial heater with conventional serpentine heating circuit. We made the sample heating circuit by printing PET film with silver nanoparticle ink. Heating paint was applied to the same PET film for a fair comparison and painted with film applicator and brush paint. We measure the minimum, maximum, and average temperature of 2 cm by 1 cm heating area with Arduino-based heat control system and custom therm camera image processing tools based on Pure Thermal 3. The experiment was conducted at room temperature without airflow. This graph shows the heating rate of the silver ink heating circuit and carbon nanomaterial heater at different low voltage. To protect the PET film, the heater was automatically turned off at 120 Celsius degree. While the average temperature of heating circuit did not reach 100 Celsius degree at 6 volts, the carbon nanomaterial heater rapidly heated above in a few seconds. At 3 volt, carbon nano heater shows more than 10 times heating speed than heating circuit to reach above 100 Celsius degree. Both brush paint and film applicator show similar heating speed. This graph shows a comparison of the heating and cooling rate at different target temperature. Since carbon nanomaterial has high thermal conductivity, both heating and cooling rate are better than silver ink, demonstrating the high power efficiency to reach the target temperature at low voltage. The narrower color band of carbon nanoheater also indicate a good uniform heating capability. While it was difficult to control the rapid heating ability of carbon nanomaterial heater, we found we can control the maximum temperature at low voltage around 3 volt by using the PID control. We empirically optimize the PID parameters and achieve the stability of the temperature with ±2 Celsius degree deviation. Next, we would like to introduce the stencil mask painting technique to create complex shape heater. We made a heater with the shape of the Chinese character heat. We use copper tape film as electrode and silk mesh as a substrate to observe the heating paint. First, we attach the copper tape film to the silk mesh with a spatula. We then use the cutting machine to make the stencil mask by cutting another copper sheet into the target shape. We manually clean the residue and use a transfer tape to attach the copper stencil mask as a positive electrode to the top of the screen mesh. We then evenly painted the screen mesh through the stencil mask with heating paint and dry it with a heat gun. We finally remove the painted stencil mask film from the copper electrode film. The resistance of the heater was measured to be 28 ohm. After applying voltage, the heater uniformly radiated heat at the painted segment and displays the design thermal Chinese character image. As another design scenario, we would like to introduce a grid array heater to demonstrate the high scalability. Inspired by the beer of the circuit board, we fabricated a compact thermal pixel using the metal eyelet and annually cut copper tape in the form of concentric electrode. We then applied the heating paint to the circular space inside the outer electrode to create 1 cm diameter heater. We applied this method to create 5x5 dot matrix heater by attaching wired eyelet to the 3D printed TPU substrate. We cut copper tape film into annular electrode array to share the electrode for each row. We use a transfer film to attach the center of each annular electrode to the corresponding eyelet positions. We then applied heating paint with stencil mask to paint 5x5 grid array with 1 cm diameter circles. We finally removed the stencil mask and placed the cover sheet to hide the electrode between thermal pixels. We built 5x5 matrix heater control system with DMX PWM dimmer and Arduino DMX shield. We control the voltage of each electrode based on 5x5 toggle switch interface. We calibrated the input value of electrode voltage to normalize the resistance difference among thermal pixels. We managed to draw alphabet letters and symbols with high response thermal pixels. We also investigated the possibility of integrating carbon nanomaterial heater in thermoplastic 3D printed structure to dynamically control stiffness. As a proof of concept, we integrated carbon nanomaterial heater in HBM structure and control the backplane stiffness by heating the central pillar. We 3D printed H-beam with thermochromic PLA to indicate thermal state and integrated with TPU frame to add shape recovery ability. Unfortunately, heating paint was not so adhesive to the plastic and cracked as the surface was deformed. Hence, we built a compact flexible heater with a copy paper and attached it to the pillar and infilled the silicone to enhance the elasticity. We measure the backplane strength at multiple control temperature with custom compression testing machine. At room temperature, the H-beam structure resisted 279 Newton load. After heating the pillar with 8 volt, the backplane strength dramatically decreased as the temperature increased and became soft enough to compress with 21 Newton at 90 degrees and recover the original shape immediately after releasing the stress. Finally, we would like to introduce multiple application scenarios. Since heating paint is flexible, we can easily prototype a flexible thermal interface with a soft material. For instance, we found off-the-cell band-aid tape is a good substrate for heating paint and facilitates low-cost fabrication of thin finger thermal interface. We also found capacitive touch sensing ability of the conductive carbon nanomaterial heater. By integrating thermochromic ink, we can create interactive thermal paper interface, such as multimodal picture and autonomous erasing paper. Carbon nanomaterial heater can also be used to control the shape of the pneumatic interface by controlling the stiffness of the 3D printed mesh exoskeleton. We fabricated an expandable 3x3 mesh exoskeleton with built-in grid array heater and control the local inflation of the silicon membrane by tuning the node stiffness with the temperature. As expected, the silicon membrane inflated differently based on the heating pattern, demonstrating multi-mode pneumatic shape change at constant pressure. The shape was fixed and reset based on the thermal state of the mesh exoskeleton. In summary, we introduced the possibility of carbon nanomaterial joule heater with rapid and uniform heating capability at low voltage. We propose a fabrication method of complex shape heater with stencil mask technique. We investigated the design of compact thermal pixel and the scalability with 5x5 grid array heater. We explored the thermal stiffness control of 3D printed structure with built-in carbon nanomaterial heater. We also demonstrated the application scenario for interactive thermal displays and stiffness control shape-changing pneumatic interface. As future work, we plan to explore the possibility of heating paint integration with some reactive actuation material like volatile liquid and liquid crystal elastomer. We are also interested in the design space of augmenting everyday object and programmable matter with digital fabrication of the carbon nanomaterial heater with smart materials. Thank you for listening.